quickly finish protein structure determination. Clearly I'm not very good at aiming this darn pen. So we already did this. That was just to kind of warm up. We already did this. So we're solving that yucky equation at the bottom when we solve protein crystal structures. So the first part of determining a protein structure by X-ray crystallography is you have to make a crystal. And often this is the stumbling block where somebody says, yep, we can't solve this protein structure because we can't get a crystal. And so how proteins are crystallized, it's the same way that if you've ever had rock candy, so you kind of dip a stick or a thread into a super saturated solution of sugar water, and then you just let it evaporate very slowly, and the crystals will nucleate and grow on the string. Okay? Same thing for proteins. So you have a very high concentration of very pure protein in an aqueous solution, and gradually the water evaporates away, and the proteins, in an ideal world, line up all in the same orientation. Okay? So if you imagine, our banana alpha helices. So if you had a whole truckload of bananas and they're all arranged in the same way in all dimensions, X, Y, and Z, now you would have a crystal lattice of bananas. Okay? So if you had a protein, you'd have a crystal lattice of proteins. They have exactly the same structure. So that's a problem because they don't. So if they're homogeneous, pure, all the same structure, and are lined up in a crystal lattice in all three dimensions, that's a crystal. Okay, so this is kind of the art form of protein crystallography. What do you have to put in there? So there's often additives like organic solvents, polyethylene glycol, which is basically a crowding agent, a molecular crowding agent. So it takes up space and forces the proteins to come together and make crystals. So again, it's a trial and error art, magic more than science. Mostly crystals still have a lot of solvent in them. Okay, and the evidence for this, so you think crystal, you think something will shatter if you drop it. So they're more like squishy, like gumdrops instead of glass or crystal. Okay, so they may still be fragile, but they're not typically brittle. They're more squishy. And so the evidence that crystals have a lot of solvent in them is that if you have a crystal of a protein that that there's some ligand that protein could bind, often when you introduce that crystal into a solution where the ligand is there, the ligand will actually find its way into the active site. Okay, so there's still enough solvent that the ligand will come into the protein, find where it's supposed to bind at a ligand binding site, and then you'd get a new crystal structure of the ligand bound form. So that says that there's enough solvent there that it acts like its normal functional self. And there's just some pictures of crystals. It's kind of cool. What's that? Rock candy protein bars. Yes, exactly. Some of them are, orthogonally symmetric. Some are needles. Often the skinny little needles don't diffract well. Yes?
Is the difficulty of crystallizing the protein directly to the size?
The size of the protein? Yes. Often bigger proteins are harder to crystallize. Also, remember how I said they all have to be oriented the same way, like a whole truckload of bananas? So if they have kind of an irregular shape, often they're hard to crystallize. It's hard for them to line up the same way. Plus, one of the problems is proteins are flexible. Okay, so it's not like a protein is a banana and you can't bend it. So proteins, in order to bind a ligand or undergo chemistry, they're flexible molecules. So how do you know that all million protein molecules in the crystal are trapped in exactly the same conformation? So if they have multiple conformations, then they don't tend to crystallize well, or even if they crystallize well, the lattice is not as pure as it should be. So that's often one of the challenges, and sometimes it's related to size. Okay, so the next step after you have a crystal is actually exposing that crystal lattice of all the protein molecules in all dimensions to an X-ray beam. Okay, and so now the X-ray beam, of course, is electromagnetic radiation. And so that electromagnetic radiation will go through the lattice with all those atoms arranged in a crystalline way, and then the light or electromagnetic radiation will go to the other side and either hit an X-ray film, back in the dark ages, or now a digital, like a CCD camera that will capture the energy, but not in a piece of film. Okay, so we can capture it digitally now. So this is an X-ray diffraction picture a pattern for DNA. So does anyone know, is this a single crystal X-ray structure or not? And whose data is this? So probably know the second question more than the first. Okay. Whose is it? Rosalind Franklin, right? Yep. Arch nemesis of Watson and Crick. In their mind anyway, not hers. And was this a crystalline form of DNA? Not exactly. So the technology was not available in 1951, 52 when this was done. So it was not what I just described for a crystal. We'll talk more about DNA structure later. But it was not all the DNA molecules homogeneously arranged in a lattice. It was actually a fiber of DNA. So right before, well, midway through the semester, we're going to isolate DNA from strawberries. Way too much fun. Someday when we just need a fun day. And you'll see that you can actually see DNA as strings of something. So if you let that dry out, that's what this was. So strings of DNA exposed to electron beam and the diffraction pattern on film behind it. It was not single molecule crystals like we would do now. So more to come on DNA. So if we have, yes?
In that last picture, you said it was a strand. Is it a strand like taken from off the strand? Or
I have no idea. Probably, so the image that you get should not depend on how the crystal is arranged. Well, so these days we would have a crystal lattice. This was a fiber diffraction pattern. I don't know how they do fiber diffraction patterns. I don't think it's end-on. I think it's side to side. But like you're not actually getting a picture. You're getting the electron beams being scattered. And so essentially every spot, and let's see if I can get a better picture of a more current. Yeah, okay. So here is what you would normally get now. So all those spots, you can see some are brighter, some are less intense. They're in different places. And so essentially all the information in those spots has to be back extracted and deconvoluted to all the atoms in the protein. So every atom in the crystal contributed to every spot on the diffraction image. That's the wacky, hard to solve problem. Okay, so back when it was diffraction patterns from fibers, I don't know how they arranged the fibers in the X-ray beam to get that. Good question. Okay, so once you have all those spots on a diffraction pattern, here's the hard part, that now we have computational tools and trial and error kind of iterative processes to try to figure out, okay, did that pattern come from these spots? So I'm going to arrange the spots and see what I get. Oh, no, we got to try it again. So there's all kinds of tricks. You don't need to know them, except to know that it's hard. So what I do want you to understand is the question of resolution. Okay, so high resolution structures versus lower resolution. So lower resolution just means you can't see things with as much detail. You can't resolve or separate things that are X angstroms away from each other. So we'll talk about the numbers in a minute, but the idea is if this duck was our starting molecule, our protein, and we collected, so this was all the data that we got from our X-ray diffraction pattern. If we only took the majority of the data, that we knew we had good data, we would still get the image of the duck, more or less. Okay? We lose some of the fine points that are probably spots out here that you can't see, but in the middle, the high intensity spots, the ones that we really know well, are enough to tell us something about the duck shape. If we throw away too much of the data, we get some kind of molecular shape, but you wouldn't say that's a duck if you just looked at it. This one, you'd probably say that's it's a kindergarten drawing of a duck, and then that's a 5th grade drawing of a duck. Okay? So the more data we have, even if it doesn't seem like it's all great data, the more fine-tuning of the structure we can obtain. And so that's resolution. So for example, here are the numbers. Don't memorize the numbers. Just know that the smaller numbers means it's a better known structure. You know the structure to more detail. So for example, again, what is the length of a covalent bond? More or less? Kind of 1 to 1.5 angstroms, right? And so if we have 1.2 angstrom resolution in our structure, that means we can see all the bonds very well. If we have 6 angstrom resolution, that means we can only differentiate things that are 6 angstroms away from each other, or 6 angstroms resolved from each other. So we can see, that it's an alpha helix versus a beta sheet, but we certainly wouldn't see the side chains resolved well. So the lower the number, the better resolution, the more we know the fine details of a protein structure. Okay, so that's the difference between kind of shape and real detail of differentiating one side chain from another. So if we go from spots, then all the computational tricks to give us electron density. So what that means is, where were there more electrons that would interact with the electromagnetic radiation? And so the bigger the chicken wire, the more electron density there was, so there was heavier atoms there. Okay, so then we go to, we can fit in, if we know the sequence of the protein, we can fit atoms and bonds in. And then, of course, what does that look like? A heme group, right? And so that's either a hemoglobin subunit or myoglobin. Okay? And so the protein becomes the crystal becomes spots, the spots become density, the density we can fit the protein backbone, the side chains, and any extra pieces in. Okay, so let me go back to the little bottom part here. So if you have a part of a protein that's flexible, okay, so if instead of a banana you had a monkey, and the monkey could hold still but his tail was flexing around. Okay, so if you had like a truckload full of monkeys, but all their tails were in different orientations, what do you think would happen in the crystal structure of the monkey?
A lot of noise.
Okay, so there's noise. In an X-ray crystallography, if you have flexible regions, you basically lose all information. So the final structure would be a monkey without a tail. Okay, because in one protein the tail is going this way and another is going this way, and essentially all those average out so that you lose the electron density for the tail region and you get nothing. So instead of getting all possible conformations, you get nothing because they kind of average out to blank. Okay, so that's kind of a weird detailed protein structure. Okay, so we already talked about crystal structures. Because there's high solvent contact, we can soak a ligand or a substrate in. Sometimes if the protein doesn't change shape when the ligand comes, now we can re-X-ray that and get the structure of the protein with the ligand bound. So now we get 2 for 1 basically. However, if the crystal cracks when we expose it to a ligand or substrate, that tells us 2 things. 1, we can't get the structure without re-crystallizing it. And 2, the protein had a conformational change when the ligand bound, and whatever that new conformation was, the protein in that new conformation didn't fit into the lattice the same way. Okay, so the protein changed conformation. That's an important piece of information about protein structure, but it means you have to go back to the beginning and recrystallize protein plus ligand from the scratch. Okay, so how do we compare NMR versus X-ray crystallography? So they both can determine structure. NMR is better for smaller proteins. Occasionally we can use it for membrane proteins. X-ray actually gives us a picture, whereas NMR gives us a whole bunch of possible structures that are consistent with distance constraints. So again, as I said, for X-ray, if we have a flexible region on the protein, for example, here, see how those 2 bits are not connected? There was a gap there. That's because that part of the protein was flexible. So here was a missing region, here's a missing region, here's a missing region. Maybe that's it. Maybe there's nothing. And in the NMR structure, I didn't erase my scribbles from last time, so you can see, there's a connection point, here's a connection, the ones that were missing before, so that was in a loop, and often those loops are flexible. So in X-ray, we might see that as 6 different possible models that are all consistent with the distance constraints, and in X-ray we see that as emptiness, no electron density, because they average out. Okay, but both are useful. The fact that they both give us essentially the same structure means that NMR, which is a solvent method, and X-ray crystallography, which is not a solvent method, are both valid and valuable structure determination techniques. Okay, so there are tens of thousands, almost 100,000 at this point, protein structures that have been deposited in a publicly accessible database called the Protein Data Bank. If you want to, you can go there and play around with it. Those of you who have Biochem Lab or will take advanced biochemistry, you'll have a chance to look at those. It's a lot of fun. So if you like to see things in 3 dimensions, you can basically pull them out, re-plot them, and kind of move it with your mouse and kind of see it and zoom in. It's lots of fun. And then people who study proteins, like me, can extract that information, and then say, oh, what would happen if we mutated this residue? Or this one seems like a good one to study experimentally. And so these days, if you solve a protein crystal structure or nucleic acid structure or combination, you can't publish a research article on that structure until you've deposited the coordinates in the public database. So it's kind of a way to prevent people from, getting information maybe that's been funded by the NIH or the NSF, so your tax dollars at work, and then not sharing that information. So this is supposed to be a publicly available database that anyone can access and that researchers have to deposit their structures into. So who do you think, or what kinds of researchers might not want to deposit their structures right away and therefore wouldn't publish research papers right away? Pharmaceutical companies, right. So if you work for Pfizer or any big research firm or pharmaceutical company, you may have research programs that never get published, okay, because you don't want people to know what you're doing until you've patented something and are pretty sure you're going to make some money off of it, okay? So if you're a pharmaceutical researcher, you do all the work, so you don't go into pharmaceutical research to get lots of publications. So what's the payoff? Money, yeah. So you either get money or you get fame, not often both, as if publishing papers gives you fame, which it really doesn't. So if you're a pharmaceutical researcher, it may be that you don't have a very big publication list, but you have patents. Okay, so you solve a protein crystal structure, your company or you think it's going to be a good drug target, and so you would patent it first. Then once you were pretty far along the line, you might deposit the structure and publish the paper, but maybe you already have a drug in the pipeline and you're kind of just getting around to saying, well, I guess we should publish this and tell the world what we're doing, but you already have a patent and you already have some hope that it's going to pay off. Yes, Tomas?
Do you get the patent, or does
Oh, the company, totally. Yep. So most companies have some kind of a bonus structure where you would get some salary bonus for patenting something. If you're a savvy researcher and business person, you would negotiate with the company that you would get some percentage of payoff. Most people in pharmaceuticals, not pharmaceutical sales, but pharmaceutical research, probably sign patent rights away and sign intellectual property rights away, so their name would be on the patent, but they don't own the patent. The company owns the patent, they just happen to have their name on it as a co-discoverer. They get a nice pat on the back, they get a nice raise, they get a nice promotion. They're not going to be millionaires, probably. In academia, so if you're a researcher here at the med school somewhere, same deal. When I came here, I signed away all my rights. If I was going to patent something, which that's not really what I do, I would then go to our office and say, well, I know I signed away my rights, but I have this great idea. Don't you want to patent it? And maybe you could cut me in on the deal. And so some people in academic research who have been successful have made a fair amount of money, and their institution makes a lot of money. So there are chemistry departments around the country where they have beautiful buildings, not here, that are not, they're not from the state government, they're not from tuition, they're from somebody's patent where the department got a huge kickback, the institution got a kickback, and they're driving a nice BMW convertible to and from, teaching freshman chemistry. Okay, I know you would like to distract me, so none of this is on the exam, but I'm so good. Okay, so we talked about protein structure. Now we're going to talk about protein function. This is just an introductory slide. We're going to start with ligand binding, moving on to oxygen transport quickly. Okay, so we've already introduced the idea of things binding proteins. So if a thing binds a protein, we tend to call it a ligand. I think you've probably heard that term before, but if you haven't, a ligand is just something that binds a protein. Typically, the charge on that thing is going to be complementary to the protein, the shape, the electrostatics. If it's a hydrophobic binding pocket, the ligand is probably hydrophobic, etc. That ligand binding might trigger a conformational change in the protein, so like we talked about for crystallography. If you solve a crystal, then soak in the ligand and the crystal cracks, you have a conformational change. And what we want to talk about next is that ligand binding can be quantified. So we can calculate and measure how tight that interaction is and how well that protein and ligand interact. Okay, so here's the mathematical part. It's not that hard. So we can write this equilibrium. So it's equilibrium binding. Okay, so it's not all or nothing. We're in equilibrium. So when you introduce a ligand to a protein that it's going to bind, you have some kind of a complex. Okay, so that's just the ligand interacting with the protein, typically in one way only. So it's not that, so probably this protein ligand complex on the right side of the equilibrium is a homogeneous arrangement. So there's only one way the ligand interacts, and so when you look at the complex, they're all the same structure. So we can abbreviate that. Protein plus ligand is in equilibrium with the protein ligand complex, and we can describe KD, the dissociation constant. So that probably doesn't look like the way you would write, an equilibrium constant, right? So if we were to write K equilibrium, you would tend to write it the other way, right? Protein ligand over protein times ligand. So what would you say about the KD then? It's just the reciprocal of the dissociation constant. It's the reciprocal of the equilibrium constant. So dissociation is the opposite of association. Okay, so the dissociation constant is the reciprocal of the equilibrium constant. Any idea why we refer to dissociation constants? I don't know either. I don't know why. I don't think it's the size of the value. I don't know if it's because what we care about is the complex. So certainly when we start talking about chemistry and enzymes, all the chemistry happens from the complex. So that's what we really care about. And then if the complex falls apart, we lose chemistry, we lose product formation. And so maybe it's just more helpful to think about starting from the complex and going backwards. I don't know. That's the only thing I can come up with. So we can quantify a value called theta. So theta is just what fraction of the protein has ligand bound to it. Okay? And so kind of where on the equilibrium are we? Are we mostly in the protein ligand complex? So most of the protein is in its ligand bound state, or are we mostly shifted to the left, where mostly you have free protein and free ligand? Okay? And so then we can kind of draw the shape of that curve. So if theta is on the y-axis, and I kind of covered up that theta, so theta, because it's a fraction, goes from 0 to 1. As we add more ligand, so as the ligand concentration increases, we get closer to 1. So more of the protein has ligand bound. That totally makes sense. If you have a little test tube with your protein, you start dropping in the ligand, the more you add, the more protein has ligand bound to it. Okay? So because it's an equilibrium, we never quite get up to 1, right? At equilibrium, there's always some free protein that doesn't have ligand bound to it. Okay? So we're going to define KD, okay, we already said it's the dissociation constant, as the concentration of ligand that gives us a protein state where half the protein is free and half the protein has ligand bound to it. So we have half free protein and half complex. Okay, and so you can kind of solve that mathematically, right? So if theta equals 0.5, then, that's not an equals, that's an arrow, then ligand equals KD. So KD has units of concentration, just like ligand does. So KD could be 2 micromolar, it could be 1 nanomolar, it could be 3 femtomolar. So it's concentration units. So just like the ligand concentration is concentration units. So if we add ligand to a final concentration of 2 micromolar, and the KD for that ligand complex is 2 micromolar, we can say half of the protein is ligand bound and half of the protein is free. So know that equation and practice it. So what does it mean physically? So KD is just the concentration of ligand that gives us half saturated protein. Let me say one more thing about that curve. So what's the shape of that curve? What do we call that mathematical shape of the curve? Not exponential. Not logarithmic. Hyperbolic. Sound familiar? Okay, it's a hyperbolic curve. And so the equation for the curve, so y equals ax over b plus x. Okay? Yes, that's right. So A is just the maximum that could be bound, and here it's 1, so that's why there's no variable there. X is the ligand concentration, B is the KD. Okay, so that's the general equation for a hyperbola, like y equals mx plus b is the equation of a line.
What was B?
B is kd. Yep. And a is just 1 because it's a fraction, you know, the maximum that you can get bound is 1, and so it's just 1 times ligand. Okay, so what does kd mean? So yes?
What did you say?
X is the ligand concentration. Yep, so as we vary X on the X-axis, you know, the ligand concentration on the X-axis, we get a new theta, so that's the Y. Okay, so the smaller the KD, the tighter the interaction. So it takes less ligand to get to our half-bound, half-unbound state. So a very small KD means very tight binding. Okay, so we have KD values that range from super-duper tiny, so that's what unit is that? Femtomolar, right? Femtomolar up to 2 times 10 to the minus 5th is, oh, come back. Is 20 micromolar. Okay, so avidin and biotin, you've probably heard of biotin, so that's a small molecule vitamin. Avidin is the protein that binds to it, and that's like the tightest natural interaction known in the world. It's crazy. Okay, so we're going to move on to hemoglobin. So kind of with that introduction, we're going to set that aside, and now we're going to talk about an example of ligand binding. So our example of ligand binding is oxygen, and that's just introductory. We're going to cover all that. So you know the most famous oxygen binding protein is hemoglobin. We're going to start by talking about myoglobin. So where is myoglobin found? In muscles. Very good. So myoglobin is famous, but perhaps less famous than hemoglobin. It's big brother. Because its structure was the first one solved by X-ray crystallography. Okay? Back in the 1950s by a grad student by the name of John Kendrew. Okay, and we're going to talk about his boss on the next slide, a couple slides later. And so John Kendrew was a grad student who was friends with Watson and Crick. Okay? And so one of the reasons that I teach biochemistry in London and Cambridge especially, is that John Kendrew worked down the hall in Cambridge in the kind of physical chemistry research lab, worked down the hall from Watson and Crick. So all these guys in the early 1950s, 50, 51, 52, like super brain power. And they were friends and tennis partners and drinking buddies and luminizers, but we'll know that today. And they were smart people kind of at the cutting edge of macromolecular structure identification. Okay, and so this was the first X-ray crystal structure that was solved. And so it looks a lot like one of the subunits of hemoglobin. We'll come back to that. And how else would you describe this protein? Based on what you know already. It's globular, so it's compact, you can say. What does it have a lot of? Alpha helices, right? Okay. So I think there are 8 alpha helices. Okay, in that globin fold. And so once that structure was solved, it was kind of given a special name. So this globin fold is seen in other proteins, and so it's it's a supersized motif. Okay, so it is the whole polypeptide, but it's seen other places, so it's kind of given a special name. Yes?
This may be a dumb question, but if something has more alpha helices, is it more likely to be globular? If it's more fibrous, it's more beta?
Not necessarily. I'll show you some other globular proteins that are all beta, but it's certainly nice if you have anti-parallel beta sheets or anti-parallel alpha helices. It's easy to fit it into a small space. So not necessarily, but it's a good question. Okay, so we have a heme group that binds iron. We'll talk more about that later. Do not learn the structure. The heme we also call a prosthetic group. So that means that as soon as that myoglobin protein is made, it picks up a molecule of heme and never lets go of it. Okay, so it's not like the heme group comes and goes from a particular myoglobin molecule. It's bound as soon as the protein is synthesized, and it stays there as an essential part of the protein for the rest of that protein's life. We'll talk about other pieces, non-protein pieces of functional proteins like enzymes that come and go, but prosthetic groups stay. Okay, so how does that heme contribute to oxygen binding? Okay, so here is the plane of that porphyrin ring system. So we kind of tilted that on its side now. And so what holds that iron atom or that ion in place? So there's a histidine residue that comes kind of from the bottom. So if this is the rest of, so if this is part of the protein, so there's a histidine that comes up kind of from the bottom plane of that heme to hold the iron in place. And then kind of on the top, so that's also part of the same protein. And then, so there's two histidines that are important for binding that iron. One that's always there. So in some books that's called the proximal or nearby histidine. And then we have another one up here that's called the distal or further away histidine. Those names don't really matter, but it is important that histidine residues are what hold that iron in place. So when there's not oxygen present, that distal histidine comes in and holds that iron. And when oxygen comes in to bind, it kind of moves out of the way and serves a more kind of remote role. Okay, so when the oxygen binds, it binds directly to that iron. That proximal histidine is always chelating that iron. The distal one kind of moves out of the way to give space for the oxygen to come in. Okay, so how can we measure or quantify oxygen binding to myoglobin? So first of all, what's the shape of the curve? Hyperbolic. Okay. And so same idea. We can have ligand binding on the x-axis, and we can have theta on the y-axis. We don't really talk about concentration of oxygen. So because oxygen is a gas, we tend to use partial pressure. It just means concentration. Okay. And so here's the weird thing. So it's the same as ligand binding, but we use different terms. So instead of concentration, we use P for partial pressure, and instead of KD, we use P50, but that really is the same as KD. So the P50 is the partial pressure of oxygen that gives us a theta of 0.5. So half the myoglobin is oxygen bound, half the myoglobin is not. Okay, so you can see it still has that same y equals ax over b plus x kind of arrangement of the equation. Same kind of hyperbolic shape. Now we get to the big brother hemoglobin. So myoglobin does not have quaternary structure. It only has tertiary structure. Hemoglobin has quaternary structure because there's more than one polypeptide. You know there's 4 polypeptide chains for hemoglobin, but only of 2 types. Okay, so there's 2 of one type, and we call them alpha, 2 of another type, and we call them beta. That's not the alpha and beta of alpha helices and beta sheets. Kind of inconvenient that they couldn't come up with something else. They're all alpha helical. Okay, so each of the subunits of hemoglobin is a globin fold protein, but it's not a myoglobin. Okay, so if you compare the amino acid sequence of myoglobin to the amino acid sequence of the alpha subunit of hemoglobin, they're going to be very similar, but not identical. So they come from different genes, so they have different amino acid sequences, but the same structure. You can overlay a myoglobin structure and fit it in, and it's going to overlay very nicely. So again, that points out that we can't get structure from sequence. So if you have the same structure, it came from 2 different sequences. They're similar, but they're not identical. Okay, and so the structure of hemoglobin was solved by Max Perutz, who was the PhD advisor of John Kendrick. Okay, so they're a research team. The PhD advisor gave his student the simpler, smaller protein to solve, so the student got there first. Once they had the structure of myoglobin and the electron density of hemoglobin, somehow through their big brains, because they didn't have computers really, they figured out, aha, it's just 4 of the globin folds in hemoglobin. So this was the second protein crystal structure solved, I think. Okay, and they shared the Nobel Prize in 1962. So Perutz and Kendrew got the Nobel Prize in 1962 for chemistry. Watson, Crick, and Wilkins got the 1962 Nobel Prize for physiology or medicine. And John Steinbeck, the writer, American writer, got the Nobel Prize in 1962 for literature. Just to round out your education today on Friday. Okay, so here's our comparison, myoglobin, hemoglobin. Obviously very, very similar structures. Not identical, but awfully darn close. Okay, so here's the good parts. We'll get to the good part at the end. So myoglobin has what kind of binding curve? Myoglobin equals hyperbolic. So what about hemoglobin? How would you describe that binding curve? S-shaped or sinusoidal? I wouldn't say that. Sigmoidal. Very good. Sigmoidal versus hyperbolic. Okay, and that is both a consequence of structure and the implication is functional. Okay, so we still can talk about theta, but now the equation of the line that gives us theta from PO2 is different. We're not going to talk about the equation for a sigmoidal curve. But what do you think it means? So we've kind of shown where oxygen concentration is in the tissues, where oxygen concentration is in the lungs. So again, where is hemoglobin found? In blood. Myoglobin is found in tissues. And so this is the beauty of the oxygen binding system, right? So when your blood goes to your lungs, what does hemoglobin say? I can bind lots of oxygen, okay? Oxygen binding to hemoglobin in the blood around the lungs is very high, so it has very high affinity. So it's very much close to, theta is close to 1, so almost all the hemoglobin has oxygen bound. So high affinity in the lungs. As that blood travels to your tissues, what happens at the concentration around the tissues? Okay, so it has lower affinity, but what about myoglobin? Still has high affinity. So again, hyperbolic shape maintains its high theta even at low PO2. So hemoglobin says, yeah, I don't really want this oxygen, you can have it. Myoglobin says, oh, I have very high affinity for oxygen even at low partial pressures of oxygen. So that's the transfer phase. Okay, so when the oxygen on the hemoglobin in the bloodstream sees an environment that's lower partial pressure of oxygen, it releases the oxygen, myoglobin takes it up. Okay, so myoglobin has a high affinity for oxygen even at very low oxygen concentrations in the tissue. So that's the transfer part. Transfer and delivery. And so what causes that sigmoidal shape? So it is called cooperativity. Okay. So cooperative binding results in that sigmoidal shape. So we're going to see more sigmoidal curves when we get to enzymes. Okay, so hemoglobin and myoglobin are not enzymes. There's no chemistry that happens in oxygen binding. It's just on or off. Whenever we see a sigmoidal shape like that, we should think cooperativity. So who can explain what cooperativity is in hemoglobin?
Isn't it where the first one attaches and that's the hardest, but as more attach it becomes easier to bind to it?
Okay, so the first oxygen binding event is less favorable, but as soon as one binds, that increases the affinity for oxygen binding to the other subunits. And the reason for that, the atomic reason that happens, is it's a conformational change. Okay, so if we look at what the heme ring looks like when there's not oxygen bound, so it's not as planar. You see how that heme ring kind of puckers a little bit? So it's not perfectly flat. It's more curved. And where's the iron in that heme ring? It's not right in the middle, so it's not centered. It's more pulled to that proximal histidine. Okay, so it's kind of pulled to the histidine. So the distal histidine that's over here just isn't holding on to it as well. So it has more pull towards that proximal histidine, towards that alpha helix. As soon as an oxygen binds, now that iron is sitting right in the middle of that heme ring, and the heme ring is more planar. Okay, so oxygen binding causes a conformational change right in the region where the heme group is, but because that histidine is on an alpha helix, that alpha helix moves location. So oxygen binding triggers a positional change of that histidine. The histidine is attached to an alpha helix, and so the whole alpha helix moves a little bit. But of course the alpha helix is connected to the rest of the protein by the polypeptide backbone, so the rest of the protein also has to adjust its shape a little bit. So that's a conformational change in the protein. And when one of the subunits of hemoglobin changes its conformation, the other ones around it are influenced and may change their conformation as well. Okay? So we call those two states, they kind of have weird names, but we're going to see this again in enzymes. So those are called the T state. So T state is inactive, and the T, this is really dumb, comes from tense. Okay, so in the absence of oxygen, hemoglobin is tensed up. Okay, so that doesn't have anything to do with conformational rigidity or flexibility, it just means inactive. And the R state means relaxed. Okay, we're going to see this again in more proteins in the future. T, inactive. R, active. T disfavors oxygen binding, favors oxygen delivery. R favors oxygen binding, disfavors oxygen delivery. Only hemoglobin has T and R states, not myoglobin. Okay, so we only get those conformational changes propagating if we have more than one subunit. So if we see that sigmoidal curve, you should always think cooperativity, conformational change, and quaternary structure of the protein. More than one subunit. You don't get cooperativity if you only have one subunit. So if we go back to our curve, okay, so hemoglobin again is the blue line. So where, if I was going to label T and R on that oxygen binding curve of hemoglobin, where would I put them? Where would you put a T? Down here. So that's the T state. So its oxygen binding is disfavored. Hemoglobin is unloading its oxygen. And the R state is up here. Oxygen binding is favored. Okay, so hemoglobin, as it sees different concentrations of oxygen, will shift from the R state to the T state, going from lungs to tissue, and then from T to R, going back to the lungs. Okay, so it constantly undergoes this conformational adjustment. Okay, and what do you see about the T state and the R states? Just kind of big picture. Okay, so there's not so much space in the middle of the R state. So we kind of collapse the core of hemoglobin in the R state. There's a bigger opening in the T state. Okay, there's some other little details. Okay, so at the interface, so in the T state, it turns out that the subunit interfaces are held together more tightly by salt bridges. Okay, so electrostatic interactions between charged groups. And this is just a schematic showing all 4 subunits. And again, don't try to memorize this, just showing that there's lots of this network of electrostatic interactions that really stabilize the quaternary structure of hemoglobin in the T state. So that's not that the subunits are going to fall apart in the R state, it's just there are different interactions in the R state. Okay, and so these conformational changes are what give us cooperativity. So one subunit changes conformation, it kind of elbows the other subunit and it changes as well. So that's why as soon as a hemoglobin binds one molecule of oxygen, now it's easier for all the other subunits to bind oxygen, and that's where you get this cooperativity. So if a hemoglobin was always trapped in the high affinity state, so if it was always R, what does it look like? It looks like myoglobin, right? There's no such thing as a T state for myoglobin. It's always high affinity. It's either high affinity or it's totally gone, okay? And if hemoglobin always looks like the T state, that's not so ideal, right? Okay, so if hemoglobin is always in the R state, that's bad because you don't actually deliver the oxygen to myoglobin, it just hangs on to it selfishly. If hemoglobin is always, sorry, that's not an R, that's a T. If it's always in the T state, it never picks up oxygen from the lungs, and so that's not ideal. So the best of both worlds, it has high affinity for oxygen in the lungs, low affinity in the tissue, that's why everything works. Okay? So again, sigmoidal curve cooperativity only possible for multimeric proteins. Okay, we're going to introduce one more topic. We're cramming it in today, it's Friday, right? So we'll continue this on Monday. to solidify it, but not introduce new material for the exam on Monday. So you'll feel better about Wednesday's exam after Monday's lecture, I promise. Okay, so the last idea I want to talk about is allostery. Very important concept in protein structure that we haven't talked about yet. So allostery can either mean other shape, or sometimes people refer to it as other site. Okay, but really what it means is conformational change. Okay, so an allosteric protein is one that binds something and then a shape change happens. Often where that thing binds is not necessarily the ligand binding site, so often what binds to trigger the conformational change is not the ligand, it's something else. But we'll get to details on that later. Okay, so for example, oxygen binding to hemoglobin changes the conformation of hemoglobin, right? So oxygen is an allosteric effector, so it affects a change in hemoglobin's conformation. So it induces a conformational change. We can call it a modulator or an effector. Okay, so it modulates or changes the conformation. It affects a conformational change. So a modulator can either be something that makes the protein or enzyme, we'll talk about that later, more active, so it's an activator, or less active, so it's an inhibitor. So again, we also could call these a positive modulator or a negative modulator. To layer on that, in case that wasn't complicated enough, a modulator could also be homotropic, which means it's the same as the native ligand. Or later when we talk about enzymes, ligand or substrate. Or a heterotropic modulator, which means it's a different molecule. Okay, so with our simple example of oxygen, how would you classify oxygen as a modulator? Is it positive or negative? Positive, because oxygen binding helps oxygen binding. Is it homotropic or heterotropic? Homotropic, because that's a natural ligand. So oxygen is the only positive homotropic ligand of hemoglobin. So it's positive because it increases the affinity for hemoglobin to oxygen, and it is oxygen. So it's kind of a silly example. It becomes less silly and less... Okay, we're going to skip that to finish up our modulator idea. We'll come back to it. Okay. Let me introduce the only other modulator I want to talk about, because it comes back to structure, and then we'll come back and fill in the blanks. Okay, so this little molecule that you can't see the name for down here, 2,3-bisphosphoglycerate. Okay, so you'll know the structure by the end of the semester. You don't need to know it for the first exam. So 2,3-bisphosphoglycerate is a heterotropic negative modulator of hemoglobin function, which means it's not oxygen. And what does it mean because it's a negative modulator? How does it affect oxygen binding? Goes from the T state to the R state. Goes from the R state to the T state. So BPG favors the T state, so stabilizes the T state. It is a negative heterotropic modulator of oxygen binding. So if you have BPG there, shift to favor the T state, disfavor oxygen binding, favor oxygen delivery. So the reason I wanted to get to this was, where do you see BPG binding in hemoglobin? Right in the core. And what did we say about T state versus R state? And the core, there's more space in that core in the T state, so now BPG fits in there and it stabilizes that T state. Okay, so in the R state there's no room for BPG, so if there's less BPG around, you can more easily get to the R state. If there's more BPG around, you fill up that hole and you're stabilizing the T state. So BPG is the molecule that you make more of when you're training for an athletic event at high altitude. Okay, so think about the physiological effect, the physiological advantage of making more BPG, how that helps you athletically. And we'll talk about that on Monday.
Isn't that performance enhancement drug?
So it's not a drug. No, your body naturally makes more of it at high altitudes.
What
I guess, I don't know if you could take it as a performance-enhancing
What
drug.
I heard, there was something report that
Oh, is it something that tests for doping? Oh, so maybe there's levels that you can get from living at high altitude, and then you can superdose, and they can pick that up.
Yeah, they used to.